Welcome everyone to processing 1 billion rows with PHP. My name is Florian. I'm working at Datadog where I'm building a continuous profiler for the PHP language. I'm also contributing to open source. That's some PHP libraries, some extensions in PHP, the documentation, also the PHP source itself. And I'm doing so although I'm married with 5 kids. So that being said, no guilt pressure. But you can contribute to open source, even if you have a lot of personal stuff going on. Okay, so enough about me. What about you? Any one of you has heard of the 1 billion row challenge? Okay, a few people, that's nice. Okay, so the general idea of the 1 billion row challenge was written down by Gunnar Morling, who's a Java developer. And his idea was to show that Java is not an IO-bound language. And the mission, should you accept the mission, is that you get a file of measurements of 1 billion rows. That's approximately 13 gigabytes of data. And you have to create an aggregated output file of that. That sounds a bit abstract, so let's dive into the details. The file that you get is a file of measurements. So you have station names, like in this case you have Hamburg, Hamburg again, St. John's, Krakow. And then they have a semicolon, and then you have a measurement, a temperature in Celsius. That can be a positive or negative floating number. There's also some details about that you should know. So the station name is defined as a non-null UTF-8. There is at least one character, so there is something to read. And it's at maximum 100 bytes that you have to read for the station name. Then there is a semicolon, and the temperature is defined as a non-null double. So you actually get something there, and it's between minus 99.9 and plus 99.9 degree. And also we get the information that there is at maximum 10,000 unique station names in there. The output that your program should create should be this aggregation here. It has to be alphabetically sorted, and the result values per station have to be in the format of minimum temperature, the mean temperature, and the maximum temperature for that station in the measurement text file. And you have to round that to one fractional digit. It wouldn't be a challenge if there is not like more rules to the game. So first of all, one definition was that there is no external library dependency. So for PHP, that means you should not just compose or require some stuff that helps you doing the work. There is one, I would say, exclude from this rule, because in PHP we have Packle. Packle brings a lot of extra stuff that could help us do these things. So I would be okay with that. The next rule is that it should be a single source file, so not like having multiple files around. Just though that it's like easier to read and easier to see what's going on in the file. And the most critical rule is the computation has to happen at runtime. So in theory, there's a few things where you can like start tackling this problem. That's you could do an analyze step before to just analyze the data, so you see how many stations are there actually, how many temperatures there are there actually negative temperature, or is this just like a rule, but it's actually not in the data set? Is there some kind of order in there that we could use? Other things to, let's say, cheat on this thing is to do profiler guided optimization, PGO, which is you write a program and then let it run attached with a profiler, and after that you feed the data from the profiler back into the compiler so that the compiler knows how the program is actually executed and optimize for that. We are not allowed to do all of these things. Okay, so with all of these rules set up, let's give it a try, I thought. So I just wrote a small program that solves the problem. And actually it's this. Who would say this is nice code? Awesome. At least one. So it's not really nice, but it gets the job done. So, okay, let's step through this. First of all, there is a stations array to just store the result that we have or that we will compute. Then open the measurements text file. As you can see, I do not check if this actually worked. I just assume it worked. And then iterate over the lanes that we have. It looks like it can just be fget CSV because it looks like a CSV file with the semicolon there. So fget CSV just reads the data and splits on the semicolon. So in $data, we're going to have $data0 being the station name, and $data1 being the temperature that we have. If that station has not yet been processed, so if you don't have that in the stations array, we just create the entry for this. I decided to go with this structure here. So basically, the array that I'm going to add into the stations array, the key will be the station name and the value will be an array with the minimum, the maximum, the mean temperature, or the sum of the temperatures and the count of temperatures, so that I can calculate the mean temperature later. In case I find this the station already, I'll just increment the counter, add the temperature that I'm currently processing to the sum of temperatures, and then I need to check if the temperature that I'm currently processing is bigger or lower than what I already have, and then like exchange the data. That's basically the loop to process the data. It's got to be sorted by station name. The station name in this case is the key, so we're going to use k-sort for this, which keeps the key value association. And after that, we just need to iterate over this and output all the stations and do one calculation, and that's the mean temperature. Because we only have the sum and the count. So we divide the one by the other, and then we have the numbers. And that's basically it. Now, people know basically people know that PHP is not a super fast language. So just imagine a number in minutes, hours, days. What do you think this program will run on the result set of 1 billion rows? And the actual runtime on this laptop for exactly this script, when I ran it the first time, was 25 minutes. Anyone impressed? Positive or negative? I thought it's pretty good. I mean, it's not bad. I thought like it would take maybe an hour, but didn't. Okay, so I was actually impressed by it not being really bad, but like I saw the leaderboard numbers in Java, and I was like, okay, they're like far away. So yeah, there's something we need to optimize here. So I mentioned I'm working on a profiler, so naturally I attached the profiler to the PHP process and observed it while it's doing its stuff. And I wanted to see what's going on in the script while it's doing, like what is PHP actually doing. And one of the things I thought initially that like it's reading 13 gigabytes of data. I'm from a century where you had like spin disks. That was pretty slow reading data, so my assumption was that it's probably spending most of the time waiting on the disk. That's not the case. You can see the CPU time is 100%, so this is a CPU-bound problem. It's not waiting on the disk. You can also see there's an idle time of 125 nanoseconds, that's neglectable, and also the file compilation at the beginning of the script of 197 microseconds, you also like don't care about this. Okay, so this view isn't really helping, but switching to the flame graph view is helping a bit, because this shows that we are spending 46% of the time in fget CSV. The rest of the time we are doing something else, such as PHP stuff going on. So I was interested in what's actually happening in fget CSV, because we're spending most of the time there. So in the beginning it looked like CSV data, because we have the semicolon there, immediately you're in this, oh, this is CSV, I use fget CSV, super easy, problem solved. One of the problems with fget CSV is that it actually implements the entire CSV spec. So it can parse closures, it can handle escape closures in a cell and all these things, and like carriage return line feeds in cells and all this stuff. fget CSV can handle all of that, and it has to check for all of the stuff when it's reading the data. But we already know by the constraints of the challenge that none of this is a thing. So I was thinking that probably it could be faster if I just use fgets and substring. Just like read the line with fgets, then find the semicolon, and then do substring for the two strings. So I did this change in the source code with the just reading fgets. The 108 bytes might be oddly specific, but that's because we know that we have 100 bytes for the station name, a byte for the semicolon, 5 bytes for the float, and then there's the carriage return line feed that we're also going to read. And so that might be oddly specific, but like that's the maximum that we're going to read anyway. Then find the position and then do the substrings. Sadly, there is in PHP, like in other languages, have this. Sadly, PHP doesn't have, there is no string slices or something that you could actually like not allocate a new string. So what's happening here is we're going to read with fgets a string, and then we're going to create 2 new strings and copy the strings around in memory, which is costly, but there is no other way in PHP. Okay, and with that change, we came from 25 minutes. Just running that brings us down to 19 minutes, 49 seconds. That's 21% less CPU time already. That's pretty nice. So what's going on? We see now that the fget CSV is basically replaced by fgets, string pos, and substring, which is okay. It looks like also visually that it occupies the same space, but that's okay. We optimize for throughput, so like these functions can do more stuff. But there's this like white spot there, this one here, where you see like there's nothing going on in like we're not calling any functions, but PHP is doing work there. So what you can do is you can go to the aggregation by line numbers, and if you aggregate by line numbers, you're going to see that PHP stops at line 18 and 23. This is like the 18 is the smaller one, the smaller span, and line 23 is the bigger span. Okay, so this is the line numbers that the profiler sees where stuff is happening. And initially it looks like in line 18 we are doing an increment, which is super easy. That's just one tick on the CPU. This can't be the problem. And the other thing is a comparison between the temperature and the station that we already have. And a comparison of two floating point numbers can also not be that complicated. So this can't be the thing that's happening here. Digging a bit deeper into PHP, what's actually doing, there's a different thing that is happening here that is wasting the time. It's not the increment that's wasting the time, but it's the access to the array. So I choose to use dollar stations and then the city name as the key. That makes an associative array in PHP. The thing is, your computer doesn't know what an associative array is. It has no idea about these things. So PHP is a nice language. It gives us all these high-level concepts. So you have associative arrays, which is not a thing actually. So PHP under the hood creates a hash map for you, and this hash map supports this high-level structure. But this also means that every time you're going to access the hash map, PHP has to calculate the hash out of your string and then do the constant lookup in the hash map to find where the data actually is. And we're doing this like a bunch of time here. So this is actually looks like one of the problems. So we can work around of this by using references. So actually just doing one hash map lookup and then store the reference to that value in the $station variable, and then just use this to work with that. And doing this brought the runtime down to 70 minutes, 48 seconds. That's 10%. That's another 10%, which we just spare by not doing too many hash map lookups. Another thing that I found when doing this was that I'm doing too much compares, probably. I thought this might be like a bad thing that I'm actually doing. Because if the temperature is lower than the minimum temperature that I have recorded for that station, it cannot be higher than the maximum temperature anymore. This is just impossible. And the other way around. So I decided to just drop this two if statements with an if and an else if. So the second condition will only be checked if the first condition didn't apply. That means we're going to spare some branches. The thing is, you could ask a question if we should do the minimum or the maximum check before, like what should we do first? We are not allowed to do any analyzation on the file, so we don't know. But probably if there is some kind of order in there, then we could choose if we do the one or the other first. But the performance improvement with that is not that big. That's just 2%. So actually, that was not like a too fancy improvement. Like it's better than jitter. You can actually measure that reliably, but it's like not really much. Okay, but there's another thing. I was saying to you that like there is floating point comparisons, and we are reading the temperature of the floating point. But actually, I looked at the source code and I found out that I did not. And there's a funny trick question for you. If you have this string variable $A with 100 and the string variable $B with 25.25, what will PHP output? Any takers? B? They will echo 25.5 bigger than 100? Because of the length string? Yeah, I'm sorry. That's a trick question. So actually what PHP will do is it will do the right thing. It will say 100 is bigger than 25.5. If you have these kind of questions, like it's like, yeah, it's a string, so PHP will probably do string comparison and look for the length of the string or check the ASCII character position or something like that, whatever weird thing. Actually, that's not the case. PHP, if both of the operands are numeric strings or one of the operand is a number and the other one is a numeric string, it will typecast the stuff magically for you and will do, in this case, a floating point comparison. So PHP has to typecast the $A and $B variables to floating point numbers and then does the comparison. Which is nice, like it helps in this problem, it actually solves our problem and it works, but it's a lot of CPU time. that we're wasting on this. So, and we are doing these kind of comparison, or the type juggling as PHP is doing for us at line 20, 21, and 23 actually. In line 20, it's casting the temp variable to a float so that it can actually add to the sum. And line 21, it has to do for the comparison. It has to convert $temp and $station0 to a float, then does the comparison, then throws away the intermediate result because it's not needed anymore. And then, oops, there's an else if. We have to convert that same stuff again to do the comparison. And when we have the conversion done, like, it's actually working, but it's a lot of CPU time. So not doing type juggling in this case is pretty easy because, like, when reading the temperature, I can just cast that to a float. And if I have that as a floating point data, suddenly there will be no type juggling anymore in the code, like PHP will not magically transfer types. And also it will use less bytes to store all these stuff, because former, the minimum, the maximum temperature, they were always strings, like whatever you do, were always strings. Okay, and without the type juggling, running the script again, just with these changes, brought me down to 13 minutes, 32 seconds. That's again a 21% improvement in performance. But there's still stuff going on, like we can still see like fget string post substring like taking over most of the time already, because this is just PHP doing its stuff. We optimized for a lot of stuff in PHP by using references and actually having our type set correct. The lines still show up because there is still work going on, but that's okay. But then when I was running the script again and trying to see what's actually going on, what can I improve more, there is something I stumbled on about CLI that I almost always forget. I don't know why, but it just doesn't stick in my mind. Something important about PHP on CLI is that you don't have opcache by default. And that's not necessarily too much a problem. Opcache does some kind of optimizations in the source code. Like it optimizes some of the opcache instructions that you have. It also caches the opcache when the PHP file is compiled, but that's not a problem here. We saw in the beginning it's like 200 microseconds, so that's a waste of time optimizing that. But with no opcache also comes no just-in-time compiler. And this is a CPU-bound problem, so the just-in-time compiler should actually be able to help there. And what you're going to do if you want opcache and chit on CLI is you need to set this opcache enable CLI to 1, which is default 0. And you also need to give the chit a buffer size. This is, by the way, a switch from PHP 8.3 or up to 8.3 to PHP 8.4. Up to PHP 8.3, the just-in-time compiler was default enabled, but the buffer size was set to 0. So without a buffer size, it's actually disabled. So to enable that, you need to give it a buffer size. With PHP 8.4, there is a change. So the chit buffer size is default set. I don't know to what, but it's set to something. And you need to set the opcache chit is default disabled. You need to set that to tracing or enable or something. And then the just-in-time compiler will run. And just with these two configuration line changes, which I think is fair in the comparison with Java and like all the rules, I think it complies. The runtime is down to 7 minutes, 19 seconds. That's like half roundabout of it. And that's pretty amazing coming from 25 minutes. I was pretty impressed by not too many complex changes, getting PHP quicker. But I thought there could be more. One of the things that I thought we could do, or one of the problems that I found is like all the Java implementations that I saw were using multi-threading. So far, this approach was using just a single thread, but in this computer I have 12 CPU cores. So it would be actually nice if I could use them to help me do the problem, or like solve the problem. So actually you can pretty easily split this problem into smaller problems and then let this run on multiple cores. This is where I need to show the source code in my editor because it doesn't fit on the slide. So let's see if this works. Wrong side. Here it is. Okay. By the way, this script will run in PHP 8.4. This is the latest and greatest. Don't run this in production yet. So there is a calculate average PHP file. You will see there is a lot of stuff in there that you already know, that you already seen on the slides. There's just a few changes. So I have the file variable set because I passed it into the threads. Then I want the usage to be that you call that, you give it the number of threads you want to run it. The more threads, the better. But if you run out of course, then the more threads will actually slow it down because your operating system will just work with switching between all the threads because there is no physical hardware left. So don't give it more threads than you actually have CPU cores. Then I passed it to an integer because having your type set is good. One thing I need to do is I wrote this function here to actually create chunks that I can process on the threads. Now the thing is I don't want all the threads to process the entire file. Every thread should just process part of the file, and after that we combine the intermediate results into the final result. So I need to get some chunks that I can work on. This function will actually do this. It will check the file size, so I have the size of the file in byte. Then I just divide by the number of CPU cores, so I have like divided by 12 in this example here. Then I have 12 chunks that I can work on. Now one of the problems that I'm left with is that I need the chunks to be aligned to the line ending because I want like that thread to read the entire line, or threads are working on entire lines. So I need it to be aligned on the line end. So what I'm going to do is I'm just like iterate over the chunks, over the chunks, then calculate a chunk end, which is just like chunk start, which is in the first iteration it's 0 plus the chunk size, which is a 12th of the entire file size. And then as long as we are not over the end or at the end of the file, I'm going to just seek to that position in the file, and then you can use fgets to read to the carriage return line feed. I'm actually not interested in the return value of fgets. I'm just interested that it moves the file pointer towards the carriage return line feed. And then with ftell, I can get the position where the file pointer now is. So I have the end of this chunk aligned with the line ending of that actual line. And after that, I have this pretty easy array with just chunk start and chunk end, which is just byte offsets from the beginning of the file to where every thread should start working on. That's basically it. And then close the file because we are nice, and then return the chunks. Now this is the function that you have already seen on the slides. This is the function that will process this chunk, this piece of the file. So whenever that's called with the file that we are working on, the chunk start and the chunk end. Also doing an fopen. This is a change because I'm going to seek to the chunk start so that I don't process the file from the beginning. And then the other change is that I need to check if I'm already reached the chunk end. So if I reach the chunk end, I can just finish the processing because like this thread is done working. The rest that you can see is just the same stuff that you've seen on the slides. There is nothing matching in here. And then there is a stations array in this function that's going to return here. That's it. So that's the preparation that I need to do in order to get this running. So then when you run the script, it calls this get file chunks function. We've already seen that. That gives me back an array of chunks. So I know that like I have 12, 10, 20, whatever, how many threads you want to start. And it has like all the chunk start and chunk ends aligned. And then we're going to do the magic, and this is this call here. So for the number of threads that you want to start, we're going to iterate over this in this loop and call the parallel run function. The parallel run function does a bit of magic under the hood for you. Actually, the run function is maintains a thread pool for you that helps you like find empty idle threads or stuff. So you don't need to actually spawn a thread. You don't need to create your own runtime and prepare all of that. You just call the run function. It will create a thread for you, or it will find one that's idle already. And then it will execute the callback that you give it. Like in this case, this is the process chunk function. You just give it the function. So we want to run this function in a new thread somewhere. I don't care. Parallel, please create a thread or find it. And then we give it the file that we're operating on and the chunk start and the chunk end. This is just the arguments of the closure that we have. And then this will just spawn a thread and do the work and start working. Also, this will not block. So the parallel run function will not wait for the result. It would give us back an object that's a parallel future. And this future holds the result of that thread. So whenever that thread or that callback in the thread returns, this future will have the result for us. So this will spawn 12 threads, one after the other, and we're going to have the futures. And after that, we need to wait for the results. And that's pretty easy because On the future, there is a value function, and the value function blocks until the result is available. So as long as that thread is actually calculating and doing its work, we are blocked here and waiting for the result. Once we have the result for this thread, we're gonna read that into our results array. You can see this looks similar to what we are doing in the main loop or in the threads when processing the data, because this is just combining the intermediate results. In this case, it's 12 intermediate results that we are combining. It doesn't matter how many, it's just like how many threads you start. And this will just combine the intermediate result into the overall result. And after that, we're going to do the same stuff as we've seen in the other slides. We're going to do k-sort and then echo out the strings. Also, there's one thing. During all of this, I noted that I wasn't using number format, so the output wasn't with one fractional digit, but was just like how many. So I added this number format here. Now the thing is, running this script, I'm not running it now, run this script brought me down in the runtime, and it brought me down to 1 minute and 35 seconds, which was pretty nice already, like really nice. You could see in the profile, you could see on the CPU dashboard that like it's working, it's doing stuff, it's actually using all the cores. That was actually pretty nice, but then I found out something. One, let's say, problem that I have due to my day-to-day job. I mentioned that I'm working on a profiler, so that's a Rust extension for PHP. And sometimes PHP seg faults if you're doing crazy stuff, and then you want to debug that. So for me to be able to debug PHP a bit easier and step debug through all this stuff and see what's going on, the PHP binary that I'm using is compiled with these two C flags. That's -g and -0. -g meaning I want the debug symbols in the binary, which just bloats it, but it makes it nicer to debug, it makes it slower. And -0 means I do not want any kind of optimization. So the C compiler that is compiling the PHP binary is not doing any optimizations. And I was like, that's probably a problem. It could be better, because like usually if you run PHP from a binary distribution, it's compiled with the C flag 02, which means like second level of optimization. I like to compile binary with -os because it's using the second level of optimizations plus optimizations that spare binary size. So that the binary gets smaller, and that means you don't have too much cache pollution. And running this script again, I'll run it now live for you, should be faster than 1 minute 35 seconds. So let's get out of this. And let's try if we can run this. So I'm using time in the beginning so that we just see how long it runs. Then PHP, calculate average.php, the PHP 8.4 with the parallel extension installed. Opcache is enabled. Keep in mind there is no just-in-time compiler on Apple Silicon so far. That's a problem. That was disabled with a pull request in PHP 8.2 something and 8.3 something. It's not there in PHP 8.4. That's due to protected memory areas. Weird stuff happening in Apple. So there's no just-in-time compiler. And we're going to run with 12 threads, if I may. Oh my God, what I'm doing? Okay, it's running. So let's wait and see how fast it actually can be. It's still thinking. There we are, 25 seconds. Coming from 25 minutes, that's nice. When I did this the first time, it was 27.7 seconds. It's probably 8.3 to 8.4, so that's another reason to upgrade to PHP 8.4 once it's out. As mentioned already, I attached a profiler to that as well to see like how the threads are doing. All the blue is CPU work. You can see in the thread activity summary below that it's 100% CPU time. It's still like, it's 25 seconds, but it's still not blocked on I/O, which is not a problem today. It's 13 gigabytes, so that's like, that's cached in, that's cached in memory already from the operating system. The last thread that you can see, there is an empty line where you see a small green dot in the beginning, a small green dot in the end. This is the main thread. So this is the creating the chunks and then in the end combining the intermediate results. So this is not something where we could look for optimization, but the threads are doing work is something where we could look for optimization. So when I had all of this together, I wrote a blog post about this, and then some people showed up with new ideas of how we could make this even more faster. And one of the things was that we were actually still doing 2 hash map lookups in most of the cases, because in most of the cases the station is already set. So there is we have this not is set stations $city, and then else we call the reference. But what you can do is you can just create the reference, because it will be null if that key doesn't exist, and then check for this, which reduces the hash map accesses from, in most cases, 2 to just 1 hash map access. Also, here was the idea proposed that we're going to read the data with fgets, and technically you could say we are reading it checked because that's the condition for the while loop. And then we have the actual condition is to check if we are between the chunk start and chunk end boundaries. The thing is, as long as we are between chunk start and chunk end, we don't need to assume that fgets will not get any data. Fgets will give us a string no matter what, because as long as we are processing between those boundaries, then everything should be okay. So we can read unchecked, and the actual condition for the loop could just be the check if we are still in the boundaries, and then progress the chunk start and just read unchecked because it should be there. And another thing was that I was reading with fgets and then string length and string parse, and I was always like, there is no string slices, this is a problem, like there should be a better way to do this, this is just like wasting a lot of time. And actually, as we saw in the profiler pictures, like this is like taking most of the time. But someone showed up and mentioned that fgets has there's another function that behaves similarly to fgets, but I wasn't aware of it, and it's stream getLine. Stream getLine behaves like fgets, but you can give it the character where it should stop reading. So using this, we could get rid of all these string parse and substring and stuff and creating new strings. So when we did all of these changes and run this again on the same machine that the Java folks were doing their stuff with 12 threads. And in the end, the runtime clocks in at 12 seconds, 12.76 seconds. Thank you. There's a few takeaways from this. First of all, the 25 minutes can totally be okay. Like honestly, I've written so many like one-shot scripts just to get some stuff done, and I would not care if I would have to do this only once and just let the laptop do the work overnight, and the next day it's there. I don't care. If it's something you run more oftenly, sometimes something really CPU intensive and you run it more oftenly, PHP actually is fast. It's not as fast as Java. The current leader in the Java dashboard is 1.5 seconds. But I think with few optimizations, we could push it below 10 seconds. And that's all, folks. Thank you very much.